Hey guys, welcome. Yeah, so in this video, I'm going to teach you a really powerful and important tool for finding the roots or the zeros of polynomials, specifically higher degree polynomials. Because, you know, if we have a quadratic, then we can factor it and solve that way. So find the zeros of the quadratic by factoring. Or we can use the method of completing the square or the quadratic formula when all else fails. And for cubics, we do have the cubic formula, which I will soon enough show you how to derive. So that's pretty exciting. But our other big strategy for cubics is factoring. But then for quartics and quintics and higher degree polynomials, factoring is like, where do we even begin, right? So factoring becomes difficult, and there's a scarcity of tools other than using calculators. One of our go-to is the rational root theorem, because it works on any degree polynomial. Yeah? Okay, and it will have a small cameo from the factor theorem, but an important cameo nonetheless, as you'll see. So let's get on with it. So in a nutshell, this is what the rational root theorem says. So rational root theorem. And what it says is the following, which is don't be crazy. No. It says that, like, if some polynomial p of x, which we can write in general as so if some polynomial like this has rational roots or rational zeros, meaning its zeros are going to look like x equals 2 or 2 over 1, because that's a rational number, or negative 1 over 1, which is negative 1, right? Or more clearly 2 over 3. But yeah, if whatever polynomial you're working with has rational roots, so roots that look like these, then they must be in the list x equals p over q. That is x equals p divided by q, where p is all factors. So the set of all factors of a0, or the constant term in the polynomial, and q is the set of all factors of a sub n, or the leading coefficient. So this is what you do. If your polynomial has rational roots or rational zeros, then you take all the possible factors of the constant term in your polynomial, and so that's the set p, and then you take all the possible factors of the leading coefficient, so that's a set q, and you divide each of these by each of these and make a new list. That's the p over q list or set, and whatever rational zeros your polynomial has, it may have more than one, they will all be in this list. So you'll see this in action in a second. But okay, so, you know, suppose that there's a bunch of numbers here. How do we check that we've found the right one among them? So this list will frequently be much bigger than the number of zeros that your polynomial can accommodate. For example, here, this polynomial can at most have 3 rational zeros. It's a cubic. And so this list might be bigger than 3, and it will frequently be bigger. And so then from this list, you got to figure out which ones are the right ones, which ones are going to work. Well, that's where the factor theorem comes into play, because, well, we're done with this. Just take mental note, and I'll, as I said, show you with those examples. Examples 1 and 2. I'll demonstrate the rational root theorem. But yeah, the factor theorem, as I said, is what's going to allow us to check which among that final list make the cut. And that's because the factor theorem says that, like, if p of a is equal to 0 for some polynomial p of x, then x minus a is a factor, and vice versa. If x minus a is a factor, then p of a is 0, right? let's quickly show, and this is tied to the remainder theorem, right? But yeah, let's quickly show why, like, for example, if x minus a is a factor, then p of a has to be 0. Well, p of x, let's say, is of degree n, then we could write it as x minus a, since x minus a is a factor. We can write it as x minus a times q of x, where q of x is a polynomial of 1 degree less than p of x, right? And so if x minus a is a factor, then we won't have a remainder because, well, if we look at p of a, that's going to be a minus a times q of a. So that's 0, right? P of a will have to be 0 if x minus a is a factor, right? Okay. All right, so this is how we're going to check using the factor theorem from that final list of p over q rational numbers. Yeah, okay, so now, as I said at the kind of beginning of the video, I'm going to show you soon enough how to derive the cubic formula. Just like how the quadratic formula helps you solve all quadratics, there's a cubic formula that helps you solve all cubics, and so I'll do a video on that soon enough, and this guy will be the example in that video. And so you'll see this guy again is all I'm telling you, yeah? Okay. But here we're tackling this guy using the rational root theorem. So we know that we need to make our list of x equals p over q, right? And so what is that set going to be? Well, let's first figure out the set p, which is all the factors of a0, the constant term. So all the factors of -4 are plus or minus 1, plus or minus 2, and plus or minus 4. Notice that I can make -4 by doing +1 times -4, or -1 times +4, and therefore why these plus or minuses are important, yeah? Okay. So this is the list P, and then this is the list Q. So the list Q is going to be, or the set is going to be all the factors of the leading coefficient, which in this case is 1. So that's just plus or minus 1. We can make 1 by doing 1 times 1 or -1 times -1, right? Okay. And then now P over Q is going to be dividing each one of these by each one of these, but there's only one of these, so it's just dividing these guys by this guy. Right, now when we do plus or minus 1 divided by plus or minus 1, we just get plus or minus 1. I'll explain a bit more detail why that is. Well, next is going to be plus or minus 2 divided by plus or minus 1. Now, plus or minus 2 is two numbers, +2 or -2, and we're dividing each of them by +1 and -1. So first, if we divide by +1, well, we get +2 and -2, and next if we divide by -1, so there's 4 total divisions we have to do, then we get +2 over here and -1, so they -2, sorry, so they swap places, but it's still just plus or minus 2, so plus or minus 2. So it's not, although there's 4 division problems, they end up being just 2 different numbers, and that's +2 and -2, and we do each one of these divided by the plus or minus. So plus or minus divided by plus or minus, I'm saying just is plus or minus. That's it. Okay. So the plus or minus 4 divided by plus or minus 1 is going to stay. Now, as I said, from here, your best friend is the factor theorem. Now, there's something really sweet about the rational root theorem, which is it would help you even with 100th degree polynomial, or like 97th degree polynomial. It will work on any polynomial, but its drawback is once you create this list, you do not know which of the rational numbers in the list is a 0. So there's a bit of guessing, but it's still worthwhile. It's still, first of all, like, great to have in a place where there's a scarcity of tools, right? And then second is, like, there's actually like an upside to this drawback, and here's what I mean. So first, the checking is very quick, because what you're doing is like each of these are possible zeros or roots, so you check P of A for each of them and see if it's 0. So for example, for 1 we do P of 1, and that's just 1 minus 15 and minus 4, and it's easy to see that that's not going to be 0. So we keep it moving quickly. There's that, right? There's that, like, kind of like, okay, it's not really a drawback. And P of 4 is the one that will work, because we're going to get 4 cubed minus 15 times 4, and then minus 4. That's 64 minus 64, which is 0. And so here's the other upside to the drawback, which is, well, now that we know P of 4 is 0, we know from the factor theorem that x minus 4 is a factor. And so this cubic is going to be x minus 4 times some quadratic. And then you could do synthetic division or long division. I have many good videos on both, so check those out. But yeah, you can now do synthetic division or long division on this cubic divided by that linear. And so if we do synthetic division, then we'd write a 4 here, and then 0 for the missing x squared term, minus 15 and 4. And what we'd find is 1, 4, 4, 16, 1. Wait, what? Sorry. 1, 0, negative 15. And this is negative 4. Yeah, that's why. Okay. So, and then this is 4, and then 0. So yeah, we do synthetic division and find that this quadratic is actually, well, its coefficients are given here. It's going to be x squared plus 4x plus 1, and then now you have a variety of tools for dealing with the quadratic. So as I said, because this cubic is going to come up again when we derive the cubic formula, I want to kind of finish solving it. And so one of the zeros is x equals 4, but the other zeros from solving the quadratic, which is x squared plus 4x. If we move the 1 to the other side, it'd be negative 1, and then plus 4 on both sides, so that the left side is a perfect square. So I'm using the method of completing the square to solve it. So it equals 3, take the square root of both sides. So x plus 2 is equal to plus or minus the square root of 3. So yeah, the 3 roots are x equals 4 and x equals negative 2 plus or minus root 3. Yeah, okay, so jot those in your memory bank for later when we derive the cubic formula. Yes, I keep saying it. Okay. So now we're on to this guy. So again, P is all the possible factors of, this time the constant term is 12, so lots of factors to list. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Okay, and then Q is, well, possible factors of the leading coefficient, so plus or minus 1 and plus or minus 2. Now, first, when we do each of these divided by plus or minus 1, well, we're going to get each of these back. And so I'll do it in 2 lines, plus or minus 1, plus or minus 2, all the way to plus or minus 6, and then plus or minus 12. So that's when we divide each of these by plus or minus 1, and then we divide each of these by plus or minus 2, and now new things show up, but also repeats show up. First, we get plus or minus a half. That's new on our list. But next, we're going to do plus or minus 2 divided by plus or minus 2. That's plus or minus 1. We already listed it. That's not new. And then next is plus or minus 3 divided by plus or minus 2. So that's plus or minus 3 over 2. That's new. You get it. Next is plus or minus 2, because it's plus or minus 4 divided by plus or minus 2. And then plus or minus 3 is next, and so on. So you don't write any repeats. In fact, yeah, I think the rest of them are repeats. So this is the entire list. Yes, now you have to guess which of these is going to work, but I'll help you out. I created this cubic, I believe, by multiplying 2x minus 3 and x squared minus 4. So if you want to like solve it on your own and check your answer, then you should know that this cubic is made this way. And of course, I needed to have equals 0 since we were interested in roots. But yeah, okay, you knew that. All right, I hope you learned a lot, and keep watching. Take care.